the higher resolution picture, what you will see is this peak, you can blow it up and you will see like, say if you blow this single peak over here, you might see something like this, or like this, or like this, or any different type of structure you can see, okay? You can see any of these structures in this one peak if you use a better resolution picture or a better instrument. Now, I am first going to emphasize on the chemical environment because that decides how many sets of protons you have. I'll make it more clear like what I mean with that. And as many sets of protons you have in a particular compound, you will have that many peaks. Okay? So let me start with the example. Take the first example here, which is 1, 2, 3, and 4 hydrogens. You just have one carbon, and all the hydrogens are the same atom at the same position. Whatever force you feel for whatever reason on this hydrogen will be the same on this one, and this one. Okay? So all of them will be feeling the same sort of electrostatic force for whatever reason it has. It means all these make one set of protons. So if you see a spectra of this one, it will be 1p. Okay, because one set of protons. Unfortunately, this one is a gas. It will be hard to grab this and get the spectra of this one. I just wanted to give you an idea of a particular set or the chemical environment. So let's move on to the second example here. Okay, that is methyl bromide or bromomethane. One bromine. I have changed one atom, but these three protons are the same. This is a single bond, and this can rotate. You have, if you remember your last conformational analysis, you were rotating along a single bond. This can rotate, and whatever effect of this one is on this will be the same on this one, and will be the same on these. So these three makes one set of proton, and these all protons are feeling the same environment because of this one. So single set. And if you remember your NMR spectra, the first question you got was CH3Br with a single peak at 2.1. Okay? I will come on that peak position and everything, but you can see these three are making one set. I will remove this arrow to reduce a little bit of ground here. So these three makes one set of protons. Okay? So you will see 1p. Now, let's come on this example. If you look on this one, hold this one as a group. Okay? I'm holding this one as a group. So what will happen is, whatever effect this one will put on this will remain the same on this one too and this one also. So whatever effect this one as a group put on this hydrogen will be the same on this one and this one too. It means these three makes one set of proton. Okay? And you will see one peak for these three protons. Okay? Now consider this half of the molecule. I would like to make clear that we are just talking about the proton NMR, so we are whatever peak we will get for the proton, that is H here. Okay? So we will get one peak for this because these are the one set of protons feeling identical forces, and hence these are in the same chemical environment. But if you look on this one now and consider the force because of this on these three protons, whatever force this group will put on this proton will be the same on this one and this one. Okay? So this one makes a one set of proton. You will see one peak for this one. Now, if you look at this molecule carefully, what you see is this group is the same as this group. Isn't it? It means the amount of force this group put on these three protons is the same as this group put on this one. It means ideally you should see two peaks. Both are both are feeling the same forces. It means both will be overlapping on each other, and you will see just one peak. Okay, you will see just one peak for 6 hydrogen because all of them are feeling the same force. They are making identical set of protons. They are in identical set, like they are in identical chemical environment. This example will become even much more clear when I come to these examples. Okay, what I mean to say will become more clear when I walk you through these examples. So just wait for a second. Now, if I am changing one atom over here, what will happen? The force because of this group here will be equal on this, this and this. But now I have changed one atom over here. So whatever force this one will feel because of this group will be the same as this one. But that the force this group has put on this one is different than what this one is putting on the top. Just because of this atom which has been changed here. Get what I'm saying? Any question?
You said there'd be identical peaks for the methane.
Yes.
But you'd be able to distinguish the two different peaks on it. They'll be overlapping.
No, they will be exactly, if I draw a line exactly on top of it, you will not see how you will identify that.
It's almost like it's...
You will get it from this integration. I will come to that point that tells you like how many hydrogen belongs to this peak. And by that number you will come to know like this is for 6 hydrogen or 3 hydrogen or 2 hydrogen. That if you look on the questions what you were supposed to do for this lab, it has written this peak is for 3 hydrogen, this peak is for 4 hydrogen, something like that. Okay? So now in this example you can see like since this atom is different, this one is putting some force on this one, and as a whole this center, this set of protons will put some force on this one. Force because of these two on these three will be the same. Force because of these three on these two will be the same. So let me say, here I'm writing 1 and 2, force because of 1 on 2. And this one, force because of 2 on 1. Okay? So there are now two sets of forces, and this one, F1 to 2 is not equal to F2 to 1. In this case, F1 to 2 was equal to F2 to 1. You know what I'm saying now? Just because of this has been changed. This atom has its own property. This is an electronegative atom. It pulls the electron from this center, and that's why this center has some different electron density than this one, and hence the forces are different now. Okay? Now look on this one, this example here. CH3, CH2, CH3. 1, 2, and 3 centers. Okay? These two hydrogens will put the same force on this one and this one. So say this one is putting F1 force, or say F2 to 3 and F2 to 1. So F2 to 3 will be equal to F2 to only 2 peaks. By looking on this molecule, you might expect 3 peaks. But if you look on the chemical environment for this one is the same as this one, and hence these 2 peaks overlap each other, and you will end up with 1 peak for these 2 and 1 peak for this. Altogether, 2 peaks in your spectrum. How it will look like? This is 0. This is 1 peak for 6 hydrogen, and this one will be 1 peak for 2 hydrogen. I am not showing the splitting yet. Okay? So please bear with me for a while. I am not showing these splitting in the peaks yet. I am just showing a low resolution NMR to you guys until unless I am coming on splitting, and I am going to explain the splitting how you are going to count for that. So let me finish the last 2 examples, and that will make it more like.
I have a question. Would it be right to say that groups with the same electronegativity create one spike in an NMR? So if they have the same electronegativity, they will create one NMR. Like how many groups there are? Like spike.
I am probably not getting your question. Can you still give me one example?
Well, because I'm looking at that, and that would be
This one?
considered a non-core molecule, correct?
Yeah.
So because both the CH3s exert the same amount of electronegativity, they have the same charge that they exert on the CH2 that has a different electronegativity. So you have 2 molecules with the same electronegativity. One molecule is different. It's like two.
In these examples, rather than talking about the electronegativity, we talk about the symmetry of the molecule. If you look on, this molecule is symmetric. You can cut it into 2 halves, 2 equal halves. So you will have the peaks for just 1 half, and the peak for the second half will overlap on each other. But now, this example, if you look on this one, we have a double bond here, and hence these 2 centers can't rotate freely. Okay? It's double bond, it is locked. You can't rotate it. But still, this atom is the same as this one, and the same as this one and this one. This molecule is still symmetric. Whatever force this one will exert here is the same force for this one. Okay? Whatever force this one will feel due to this one because of the diagonal distance, the force will be the same for these 2. So altogether, this molecule is symmetric and the forces are the same. All the centers are feeling the same forces. It means these 4 protons will make one set of protons, and you will see 1 peak. Now I have changed this over here, and keep in mind, look on this example very carefully. That will make everything very clean and clear. You can't rotate these 2 bonds, these 2 centers, sorry. Now, this one is close to this atom in space. This atom is far from this one. Okay? Now consider the forces on this one. This one will feel a force into this. This one will feel a force into this one. Okay? Force on this one, 1 and 2. Now, the distances are different, forces will be different. So what you will see is how many protons are now in this molecule. There are 3 protons and 3 different sets. So you should expect 3 peaks. Peaks for these 2 will be really close. Okay? And this one, peak for this one will be little far. So now you can see what I mean from the chemical environment. You have to literally see whether the molecule is free to rotate or not. And if it is free to rotate like this one, the forces due to this one will be averaged out on each of these. So these will be like giving you 1 peak. But if the molecule is not free to rotate, the peaks will be different or little different. If it is not different drastically, it will be little different. Clear? So that is all about your chemical environment. Now we can move a little faster.